Welcome back to the most significant bit. I'm your host Mahit, and today we're talking about something you probably never thought about. Shark skin, and how a handful of researchers turned it into one of the more quietly influential ideas in modern design. Here's where it starts. Hospitals have a persistent problem: colonizing surfaces. More specifically, these include doorknobs, bed rails, countertops. Anywhere hands touch, bacteria build up into biofilms, and these biofilms are hard to kill even with aggressive cleaning. For decades, the answer was chemical, harsher disinfectants, antimicrobial coatings loaded with silver or other agents. That works, but it comes with a cost. Bacteria can evolve resistance into chemical treatments the same way they evolve the resistance to antibiotics. So the question researchers at the University of Florida started asking in the early 2000s was different. What if you didn't need chemistry at all? What if you could stop bacteria with shape? This question led them to sharks. If you run your hand along shark skin, it doesn't feel smooth, but it almost feels like sandpaper because it's covered in tiny tooth-like structures called dermal denticles. Each one is rigid, and these ridges are arranged in a specific repeating diamond pattern. Sharks didn't evolve this for bacteria, though. They evolved it to reduce drag in water and to deter algae and other small organisms from attaching to their skin. But the mechanism turned out to transfer almost perfectly to a different problem. The same microtexture that keeps a shark's skin clean of algae and also makes it physically inhospitable for bacteria to settle on. This is the core idea of biomimicry. You're not copying an organism because it's clever, but you're copying it because millions of years of selection pressure already solved a problem that's structurally similar to yours. A biologist named Tony Brennan, working on a Navy-funded project to stop algae from fouling submarine hulls, noticed sharks were one of the only large ocean animals that stayed algae-free. He modeled the denticle pattern mathematically and found the specific ratio of the diamond geometry, width, height, and spacing that made these surfaces resistant to organisms trying to attach. That pattern became the basis for a synthetic surface called Sharklet. The Navy application didn't fully take off, but the underlying discovery that surface texture alone, no chemicals involved, could deter microbial attachment, and this was way too useful to stay in one lane. Sharklet Technologies took the pattern and applied it to healthcare. They engineered a micro-textured film embossed with the same diamond geometry that could be applied to high-touch surfaces. This is again door handles, IV poles, bed rails, touchscreens, you name it. Studies showed that it could reduce bacterial migration and colonization on these surfaces significantly compared to smooth plastic. Again, with zero antibiotics, zero silver ions, nothing for bacteria to adapt around. Because the effect was purely physical, resistance isn't really a viable evolutionary response the way it is to a chemical. What's interesting is that the pattern didn't stop at hospitals. The same drag reduction property that helps sharks swim efficiently turned out to matter a lot to an industry obsessed with efficiency: aviation. Riblet films based on the same shark denticle geometry have been tested and in some cases applied to aircraft fuselages and wind turbine blades. Airbus and other manufacturers have experimented with riblet surface films that mimic shark skin texture to reduce skin friction drag, and even a small percentage reduction in drag translates to a meaningful fuel savings at the commercial scale. So the same biological pattern is simultaneously fighting bacteria in an ICU and cutting fuel costs on a long-haul flight. Two industries that have almost nothing in common, solved by the same piece of shark anatomy. What I like about the Sharklet story is that it's a clean example of what biomimicry really is versus how the word sometimes gets used. It is not nature is inspiring, therefore inspired design. However, it's a specific, measurable geometric pattern, reverse engineered from a real organism, validated mathematically, and then deployed across industries that share an underlying physical problem: surface interaction. Even though on the surface, hospitals and airplanes look nothing alike, that's the pattern worth remembering. The best biometric designs usually come from someone noticing that two very different problems are underneath the same shape. That's Sharklet, and that's the episode of the most significant bit. Thanks for listening, and I'll catch you on the next one.